Lecture 8. Lie derivative in terms of Lie bracket. We will define the Lie bracket. Let's show that covariant derivative is given by this relation here. See? This I call equation 1. You see, I already derived a covariant derivative in the beginning of this series of lectures. You see? Just you can find this derivation there. So let's write here. This is K. This is I. This is J. Okay. This is I. Now this is equation 1. Let's prove this. Let's prove. We already did, but let's repeat the derivation. Consider covariant derivative. You see this covariant derivative. The vector y is yj partial with xj. So this is an abbreviation of this notation. So expand this product, okay, just leads to the right hand side, quite easy. So then I have derivative of this times this plus this times derivative of this. Relabel the index j and k in the first term over here. You see, I substitute j by k. This is k. So this leads to this relation over here. You see, they're the same k. I just relabel. I substitute j by k, and then I combine, you see, and leads to this relation, which this is a partial of y, xy. This actually is xy, partial of xy, y, k, the components, k, this is a base vectors, okay? So let x, see, xi partial of xi. Now I can do the same. It's analogous. You see, you just substitute xi here. This substitute the partial I here and multiply by xi. You see, that's quite easy. You see. From here, I can obtain this. Now, this is a vector, xi. This is in this case, is the basis. Okay? Now, so I can do this relation here as the k. This is the free index k, and I is dummy, and j is dummy. So I can change this instead of k, I set I, this m, xm, see, this I. Here is I is the free index. You see, I just copy from here to here and substitute k by I. See, m is dummy, okay, j is dummy, and k is dummy. So this I is a free index. I call this relation 2. Analogously, okay, instead of y here, I set x, the tangent vector, and this is y. You see, you just look at here and look at, for instance, here, you see, I just exchange x by y and y by x. And then I'll write this. It's developed. This is the same relation, it's analogous, okay, relation here. Now, I assume torsion free. What means torsion free? The Christoffel symbols, they are symmetric with respect to the lower index, kj, jk. They are equal, you see. When this happens, the hypothesis, I say that it is a torsion free. We'll talk torsion in later videos, see later classes. Now this equation 3. See? Now define the Lie derivative. You see, the intention here on this definition is just to eliminate the connection. Why? Connection is a Christoffel Symbols, is a connection, is related to parallel transport. And the Lie derivative is related to the push forward. You see, that's why this definition, okay, if you subtract 2 by 3 and 3, you see easily that the torsion-free hypothesis, this will cancel. You see, because J is dummy and K is dummy. I can, you see, substitute here. When I subtract, I eliminate, I cancel these two terms over here. So this lead, the definition, Lxy, this is a component, the ith component. In 3 dimension, I is equal 1, 2, 3. In 4 dimension, I is 0, 1, 2, 3. As it will appear in relativity theory. So, but this I is equal 1, 2, 3 in 3 dimension. You see, I just set this negative sign. I already cancel, you see, the connection. There is no connection here. So, this I define as the Lie bracket, xi, and the component of the Lie bracket. Now, there are a lot of properties of the Lie bracket that we'll mention later, okay? That's very important. The first one you can see easily, that is skew-symmetric, because if I permute x and y, this sign here will be plus and this will be minus. So you see a lot of properties of the Lie bracket. Okay, that's then we get to prove, to get the Lie derivative in terms of the Lie bracket, which is the purpose, the objective of this lecture. Okay.